Hello viewers, welcome to my channel. Today we want to look at chemical equilibrium. What do we mean by chemical equilibrium, or that a reaction is in equilibrium? A chemical reaction is in equilibrium when the rate of forward reaction and the rate of backward reaction are equal. You can also say that a reaction is in equilibrium when both the concentration of the reactant and that of the product are constant, not equal, note, not necessarily equal, but constant. Examples of reactions, reversible reactions. Examples of reversible reaction. Number one, hydrogen gas reacting with nitrogen gas to form ammonia gas is a reversible reaction. You don't use single arrow. Single arrow means that the reaction is not reversible. But you use double arrow like this to show reversibility. To balance the equation, ammonia is, hydrogen is 2 here and 3 here. Ammonia is 2 and 1 here. You make it 2. 2 times 3 is 6. Hydrogen is 6. Hydrogen is 6. So to balance hydrogen, you write 3 at the back. So this reaction is reversible. How do we mean that this reaction is reversible? It means that the rate of formation of ammonia is equal to the rate of formation of the reactants. It also means that as these reactants combine to form ammonia, ammonia is also decomposing to form back the reactant. And that is what we mean by reversibility. And at a point, the rate at which these two things combine to form ammonia and the rate at which ammonia reacts to form back the reactants become equal. So at equilibrium, R1 is equal to R2. The rate of formation of these products is equal to the rate of formation of these reactants, irrespective of their concentration. Number two, ammonium chloride solid undergoes reversible reaction also to form ammonia gas plus hydrogen chloride gas, where R1 and R2 are equal. At equilibrium, R1 is equal to R2. There are so many reversible reactions that are difficult to attain equilibrium. Example of such reaction is photosynthesis, where water combines with carbon dioxide to form glucose and oxygen. This reaction is reversible, but it's difficult to attain equilibrium because the reaction happens in an open system. As glucose is formed, oxygen escapes into the atmosphere. Therefore, there will be little or no oxygen to recombine with the glucose to form hydrogen and carbon dioxide. To balance the equation, carbon is 6 here, so you write 6 at the back of carbon dioxide. Hydrogen is 12 here, you write 6 at the back of water. Oxygen, 6 plus 12, 18. 6 plus, you make this place 12 by writing 6, so it's balanced. So, this is photosynthesis. The reversible reaction is where oxygen combines with glucose to form back this, but it only happens separately in the body of animals and plants during cellular respiration. But this one happens in the body of chlorophyllous plants, the forward reaction. So this one is difficult to attain equilibrium because of these factors I mentioned. Okay, graphically, let's represent reaction equilibrium with a graph. This is concentration, and this is time axis. Now, let's take reaction 1. Let's take reaction 1. Hydrogen plus nitrogen to yield ammonia. And ammonia to yield hydrogen and nitrogen. What this graph shows is that we have two reactions. The reaction that produces the product ammonia and the reaction that produces back the reactants, hydrogen and nitrogen. So in these two graphs on this sheet of this plane, this graph shows the forward reaction where hydrogen and nitrogen combine to form ammonia. And this one shows backward reaction where ammonia reacts to form hydrogen and nitrogen back. So what happens? In the beginning, at the beginning, concentration of ammonia is 0. Look at it. Concentration of ammonia is 0 when reaction begins. And concentration of hydrogen and nitrogen are positive. That is the beginning. Because when the reaction begins, there is no product. As the reaction proceeds, the concentration of the reactants keeps decreasing. If you follow the graph, you see that concentration keeps decreasing with time. Until, as it is decreasing, the concentration of the product ammonia, which was 0, starts increasing because it's now being formed. So, as ammonia concentration keeps increasing, it will start reacting to form back the reactants. And at a point, as the reactants, the concentration of the reactants keep decreasing and that of the product keep increasing, a point will reach when the reaction, the concentrations become constant with time. There is no change in concentration. So at this point, we call it points of equilibrium. Point of equilibrium. Okay, we also have another graph where the concentration of both reactants and products are not necessarily the same, but they are constant and equilibrium is reached. Look at this graph. Look at this one. This is a graph for reaction of the products to form the reactants. And this is the graph for the forward reaction. If you look at this graph, the difference is that at equilibrium, the concentration of the reactant, the concentration of the reactants reaches a constant value here. Where there is no decrease anymore, we have constant concentration. And here, we also have constant concentration of the products, but the two concentrations are not equal. Here, concentration of the reactants, that is hydrogen and nitrogen, their concentration here is greater than the concentration of the product, which is ammonia. But here, concentration of the reactants is the same as concentration of ammonia. So what do we make out of these two graphs? The concentration of reactants and products at equilibrium may not necessarily be the same. They may be different, but what is certain is that the rates at which the reactants form the product and the rates at which the products form the reactant must be equal for equilibrium to be attained. So now let's look at conditions for equilibrium. Conditions for a chemical system to reach equilibrium. Conditions for equilibrium. What are the conditions for equilibrium? Number one, the reversible reaction must be occurring in a closed system. What do we mean by closed system? A closed system is a system that does not allow particles to pass through it. For instance, if you are heating ammonium chloride, you are heating it. It's a reversible reaction. It's a reversible reaction. If you are heating this to form ammonia and hydrogen chloride, it may not necessarily reach equilibrium. This is the test tube. It cannot reach equilibrium if the test tube is open. But if you cork the test tube, you cork it, the test tube becomes closed system. This is open system. Now, this is our ammonium chloride. This is our ammonium chloride. In an open system, what happens? Once you heat this, the ammonium chloride will decompose to form ammonia, which is a gas, and hydrogen chloride, which is a gas. These gases will keep escaping. So their concentration will not be increasing because they will escape the system. And there will be nothing like constant concentration. They will keep escaping. The gases will keep escaping until the concentration here becomes zero. But here, as the gases are being produced, there is no route for escape. So what happens is that the gases will start recombining to form the products again. So as the products, to form the reactant. As the reactant disintegrates to form the gaseous products will recombine to form the reactants again because the system is closed. Now let me ask, why is it that the photosynthesis, which is reversible reaction, does not reach equilibrium easily? This is a plant leaf where photosynthesis is likely to occur. So what is inside the plant leaf is water and the carbon dioxide. So when they react, they give you glucose with oxygen, which is a gas. This gas will keep on escaping, so that there will be no oxygen gas to recombine with glucose to form back water and carbon dioxide. So the photosynthetic reaction happens in an open system. That is why the reversible reaction cannot easily reach or attain equilibrium. Please drop your comments. If you have any question, you can drop it at the comment section. Meet you in our next class.